Hi guys, it's George again. Okay, so in my last video we went over the 0th law of thermodynamics, and continuing with the series, now we're going to go over the first law. So we have the first law of thermodynamics. This is also known as the fundamental law of thermodynamics, so you can probably guess that this one is pretty important. And what the first law says is that energy cannot be created or destroyed. It can only change form. And this is probably not the first time you hear this statement. This is also known as the law of conservation of energy. And what I'll be trying to do in this video is break this sentence down, and I'll also be giving you some intuitive examples of what this law means. Okay, so I think a good starting place would be to define exactly what we mean by energy. And believe it or not, energy is not the simplest thing in the world to define. It's actually a pretty abstract concept. So for the sake of time, I won't be explaining exactly what energy is, but I will be providing you with a working definition of energy. Okay, so we have defined energy as the ability to do work. This is probably the way you will see energy being defined in most thermodynamic textbooks, and I think this is actually a pretty intuitive definition of energy. Like when we use the word energy in everyday language, like for example, when you say, I have a lot of energy right now, what you are saying is that there are more things that you are capable of doing right now, that your ability to do work is higher right now. And subsequently, when you say you don't have a lot of energy, you are saying that there are fewer things that you are able to do. So I think this definition is fine. It correlates with what we mean when we use the word energy. Okay, so we have a working definition of energy, so let's look at the rest of the sentence. It cannot be created or destroyed, it can only change form. So I think the best way to demonstrate this is to just give you some examples of this happening. Okay, so let me go ahead and clear this really quick. Okay, so now that I have a clear canvas, let's see what we could draw here. Okay, so let's say I have some cliff, and this is the ground. And let's say that on top of the cliff, I have a boulder. So there's my boulder. And my question is, does this boulder have any energy? Well, the boulder's not moving, so it doesn't have any kinetic energy, but there is some distance here. There's some distance between the boulder and the ground, so you would say that this boulder does have some potential energy. And it has potential energy because let's say that the cliff face would somehow break off and the boulder would fall, then this boulder would have a lot of potential to do work. Like this breaks off, the boulder falls, and when it hits the ground, it would hit with a lot of force. And it would hit with this much potential energy. Whatever potential energy it had at the top. Okay? So let's say exactly that same thing happens. Let's say my cliff face breaks off and then my boulder starts falling. Boulder starts falling. And eventually it hits the ground. Okay? So let's look at this distance. Here at the top, my boulder had a lot of potential energy. And let's say I calculated using the mass and using the gravitational constant and using this distance. Let's say I calculate it, and let's say I get a number like 10 joules. We use the unit joules to calculate energy. So let's say it's 10 joules. Okay. So here at the bottom, we don't have this distance anymore. So here, we don't have 10 joules of potential energy. We actually have 0 joules potential energy. But the first law of thermodynamics says that energy cannot be created or destroyed. So what happened to my 10 joules? My 10 joules had to have gone somewhere. Well, what was happening is that as the boulder was falling, thanks to the Earth's gravitational field, it started picking up some velocity. So here the velocity is a little bit bigger, here the velocity is a little bit more, a little bit more, a little bit more, and here the velocity is as great as it possibly can be. And if you calculate the amount of energy down here using the equation for kinetic energy. And I won't do that in this video, maybe in another one. But let's say you calculate the energy at the bottom. It would be roughly about 10 joules. Because all the energy up here was being converted from potential energy over to kinetic energy. And the reason why I say it's roughly about 10 joules is because as it was falling, it was going to be hitting air molecules. It was going to be met with some resistance. So those air molecules would have taken some of the energy and they would have heated up and they would have taken some of that energy. So again, the energy is not lost. The energy is all there somewhere, but it's being transformed from potential energy over to heat with the air molecules and over to kinetic energy over here at the bottom. So like the first law was saying, energy cannot be created, it cannot be destroyed, it can only change form. So the energy was going from potential energy to other forms of energy. Okay, so let me try to give you another example. Let me clear this. Okay, so let me give you another example here. I'm going to draw a piston. There's my piston. And I'm going to draw it around right there. And I'm going to draw a gas in here. So let me draw some gas molecules. Okay, so there are my gas molecules. And now let's say I'm going to add some heat to my system. So let me add some heat. And we actually don't use the letter H to represent heat. We use that for something else. We actually use the letter Q. Don't ask me why they use the letter Q, but that's the letter they use. Okay, so I'm going to add some Q to my system. I'm going to add some heat. And what this is going to do is that this is going to increase the amount of energy in my system, right? So my system had some energy before this, right? And we use a letter to represent that energy. We use the letter U. And this represents the internal energy of the system. And this includes things like kinetic energy. So these molecules are moving around, they're vibrating, they're bouncing off walls. So that includes that, and there's other forms of energy. There's potential energy, there's energy between the bonds of the atoms. So there's a lot of energy in here. We're going to take all that energy and we're going to call it internal energy. We're going to call it U. Okay? So what's going to happen is that my heat going into the system is actually going to make these molecules vibrate a little bit more, right? So it's going to increase their kinetic energy. So what's going to happen is that these molecules are going to start bouncing off the walls, right? They're going to start bouncing off the walls a little bit more than they were right now because the kinetic energy went up. So they're bouncing off these walls. And what's going to happen is that if we look at what happens at the end of this process, let me draw another piston over here. And we draw it somewhere around here. That seems about right. Okay, now let me draw my gas again. So, well. Okay, so here's my gas. Okay, so let's go through what happened here again. I added some heat to my system. This increased the internal energy of my system, which includes kinetic energy, and that kinetic energy made these molecules bounce off the walls a little bit more, so it was increasing the pressure inside this piston, and it raised my piston from here to here, right? So you could say that my system did my gas molecules did work on this piston, right? So we started off with heat, which is a form of energy. It has units of joules, just like any other form of energy. Increased the internal energy of my system, did work on my system, and that also has units of joules, so it's also a form of energy. And now my piston went up. So now we have some potential energy over here, right? So, and this is a perfect example of the first law of thermodynamics. We start off with one form of energy, heat, and then we get kinetic energy out of that, and that does work. And then now at the end of the day, we have some potential energy. And this is exactly what the first law of thermodynamics is saying, that energy cannot be created, it cannot be destroyed, it can only change form. Okay, let me clear this one more time. Okay, so this is ultimately how I like to think of the first law of thermodynamics. Let's say we're looking at our universe. Okay. And let's say that our universe has 1 million joules of energy. So 1 million joules of energy. And our universe doesn't have 1 million joules of energy. It has a lot more than that. But let's just say that our universe has 1 million joules of energy. And let's say we're starting our day on, what's today? August the 10th, 2014. So let's say at the beginning of the day we have 1 million joules of energy, and throughout that day there were going to be stars collapsing, creating supernovas, and there could be galaxies crashing with other galaxies, and there could be asteroids crashing into planets. There's going to be a lot of energy being transferred, right? So let's say at the end of the day, let's say the start of the new day, August 11th, 2014. How much energy will my universe have the next day after all that happened? Well, it's still going to have 1 million joules of energy. This number cannot change. Remember, energy cannot be created and energy cannot be destroyed. This energy, this number of the amount of energy the universe has will always remain at 1 million joules, no matter what happened. No matter what happened the previous day, no matter what happened the previous week, this number will always remain at 1 million joules. And that's what the first law of thermodynamics is saying. The universe has a set amount of energy, and that amount of energy will never go down, and it will never go up. Alright, well that's pretty much it for this video, guys, and I hope you liked it. See you guys in the next one.